Hello, we are Group 10. Our project is Infrared Vibration Sensitive LED Drum and Metronome, aka LUDS, Light Up Drum System. And we are four group members Aaron Holloway, who's EE in Power Track, and myself, Ajay Natanme, also EE in Comprehensive Track, and Elisha Peterman, also EE in Comprehensive Track, and Malcolm Donaldson, who is Photonics major. And our project consists of a drum in which we attach infrared sensors on its circumference, and it detects the vibration based on the drum beats, and it outputs signals to the LED and display. And the details are shown on the following slides.
Our task distribution is that Aaron Holloway, as the power track, will be working on the power supply. Ajay, as the most experienced with computer programming, will work on the software design and microcontroller. Elijah will work on the LED array and user interface, and I will work on the IR sensor array. Our our core goals can be summed up as the LUDs will take inputs from the drum beats and user interface, process them on the in the MCU, and then output those calculations as flashes in the LEDs. Our advanced goals are to add some customization options, such as changing the LED colors or creating an automatic replay function, or adding polyrhythms. Our stretch goals are to incorporate the LUDs into a full drum kit and to generate MIDI files based on replay data. Our core objectives will be to use a combination of IR sensors, an LCD screen, and knobs and switches to act as input, and that will feed into the microcontroller, which has an clock function in interrupt mode to register inputs. Then the LED strip will be attached inside the drum and will flash accordingly. We will also have a power supply that operates on both an AC adapter and a rechargeable battery. The advanced objectives are going to be achieved using additional switches and knobs on the user interface, and the LUDs being integrated into a drum kit will consist of 8 pieces, 5 drums and 3 cymbals, and the replay data will be saved or converted into a musical instrument digital interface file or a MIDI file, which is ready to be played as music. Our engineering specifications are things like the size of the drum, how much power should be drawn from the DC power supply, the frequency of the clock, the range of the sensors, but our key specifications are that the LUDs should allow for a minimum of 400 LED flashes per minute with a metronome timing error of less than 2%. The reflectance sensors must detect vibrations between 140 and 200 hertz in frequency and moving at 900 or 93 meters per second. And the LUDs will be designed to operate using both a B-type AC adapter or a rechargeable battery with a minimum battery life of 2 hours.
Here we have the project diagram. To the left, we see the various inputs for the LUD system, which include the infrared sensor, the flash and fade switch, for instance. Above, we can see the power-related components, which include the AC to DC converter, power supply, and battery, as well as the MCU and how it coordinates with the power amplifier going to the LED strip. As well, the components are designated by the various colors in the legend.
The basic layout of the device will be attached to a drum, where the LED array strips will be placed through a double-sided tape on the inside of the drum, and then six sensors will be placed on top of the drum, and three sensors will be placed underneath the head of the drum. Those sensors and the LED strip will be wired to a nearby control box, which houses the user interface and the MCU.
So here we have the power supply design, which is mainly composed of four components: the AC adapter, the battery, the power switch, and the voltage regulator. Here we also have the non-inverting amplifier, which is also powered from the switch. The 12-volt regulated DC power supply, either from the battery or adapter, is sent to the power switch, which is regulated for the incoming power. The DC signal is then sent to the voltage regulator and non-inverting amplifier. The voltage regulator is necessary to step down the voltage to a suitable level of 3.3 volts, which is the input for the MCU, so that it may operate. The non-inverting amplifier is responsible for amplifying the signal coming from the MCU to the LED strip. Here we have the voltage regulator schematic from our Eagle software. As you know, the regulator is responsible for stepping down the voltage from 12 volts to 3.3 volts. The converter chip used for this voltage regulator is a synchronous buck converter named the TPS 563212DR LR. Here we have the voltage regulator schematic. Here we have the power in, designated by the name to the left for the regulated 12-volt DC source, and to the right we have the output of the regulated, designated as VCC. Up next is the battery component selection. Here, the battery utilized for the LUDS device will be the 18650 battery pack from Battery Int. The battery pack is of lithium ion and is rated for 6,000 milliamps with a voltage of 12 volts. The average current consumption from this project is about 2.147 amps, enabling the battery to have a battery life slightly over 2 hours, which is above the projected amount of time, priced at $23.99. Next is the power switch component. The power related switch used for the LUD system will be the 840315 RNZQ. It is a 3-position 4-pole switch, which allows the user to switch between two power sources and turn the device off safely. Next would be the AC adapter. The AC adapter is a 12-volt 4-amp AC to DC converter made by CoolMC. Along with the AC adapter comes a DC connector, allowing for loose leads to another potential connection.
And the sensor design, it will be twofold. First half is the reflectance sensors under the skin of the drum. They will place directly under the skin of the drum at a distance of about 3 millimeters, and they will use reflection to detect the vibration, and the 6 sensors will work in conjunction to calculate the origin point of each vibration. Then there are the beam break sensors on the outside of the drum, placed in a ring. These will be used to calculate the velocity of a hit with the drumsticks, which will in turn be used to calculate the force of each hit. The component selection for the IR sensors was pretty simple. The reflected sensors, there was really only one choice, the QRE1113s, which were the first sensor that we picked out. And despite our research into other sensors, still won out in the end in being both the most cost-effective at about $1.50 and power efficient, being the most power-efficient choice. The beam break sensors will be OPB856Zs. Unlike the QRE sensors, which must be analog to capture varying light levels, these sensors will only have to detect whether light is on or off, and thus can be digital. Originally, we were going to go with the OPB100Zs, which were more of a cost-effective option, but the 856s were had the unique casing seen in the photo above, that made it conducive to the LEDs or the LUDS designs. And despite being less cost effective, we went with those instead. They were about, I believe, somewhere between $5 to $10 a piece.
The LED design consists of 4 parts. The first part is the signal coming from the MCU to tell the LEDs when to turn on. That signal leads into a non-inverting amplifier, which amplifies the 3.3 volt signal to the 12 volts necessary to light up the drum kit. Or the signal then goes from the amplifier to the dimming module, which allows the user to control the color and the brightness of the LED array. And then finally, the signal moves from the dimming module to the LED strip, lighting up each of the LEDs. In this slide, we have the calculations for designing the amplifier. Here we can see that the gain is equal to 1 plus the ratio of the R1 to the R2 resistor. So the R1 resistor was chosen to be 2.6 kilo ohms, and the R2 was chosen to be 1 kilo ohm. Here we can see the circuit for the non-inverting amplifier on the left, and on the right we have the AC sweep showing that the circuit does not attenuate the output until reaching to about 1 megahertz, which is far beyond what will be needed for this project. Here we can see the PCB schematic for the non-inverting amplifier made in Eagle. Next, we have the component selection for the amplifier. We went with the TL084CN because it has 4 potential circuits that can be hooked up to. The main positive thing about this component is the high slew rate of 13 volts per microsecond, which is great to reduce any latency caused by the amplifier. Has a supply range of 10 volts to 30 volts, and we're going with 12 volts. It has a small offset voltage of 3 millivolts, which should be negligible for this project, and it costs only 62 cents. Next, we have the component selection for the dimming module. Both dimming modules were pretty similar in having flash, strobe, smooth, and fade features, costing pretty similar amounts, having 5 levels of brightness. But we did end up with the dimmer-3CH because it allows the user to actually program its own combination of RGB colors, allowing for literally millions of different color choices. Next, we have the LED strip component selection. There were 2 main strips that we're deciding between. The first was a forward-emitting strip at 60 LEDs per meter, 120 lumens per meter, 12-volt power supply, and we ended up going with the forward-emitting because the other choice was the side-emitting, and the side-emitting shoots the LEDs out the side of the strip, which would then in turn be shining into the eyes of the drummer. So we went in with the forward-emitting. Here we can see the basic design of the user interface. This is the box that will house all of the components besides the LED array and the sensors. On the top we have the LCD display, which will show which features are currently active. And then you can see a switch that will switch between the sensing mode and the metronome mode. And each of those sections has the switches and knobs to control the parameters of each of those modes. Next, we have the switch component selection. We chose this switch because it is a dual position or single position dual throw switch. Dual throw because all of the options we have are either or options, meaning one feature is on or another feature is on, versus a feature that's on or off. So that's why we went with the dual throw. The price of this is $2.88 per switch, and it has a lifetime cycle of 20,000 cycles. Next, we have the switch pull-down resistor schematic. we can see these X's show where the switch will be soldered onto the PCB board, and then the resistors below are the pull down resistors to ensure a good connection. Um, Next, we have the knob component selection. The features of the LUDs are discrete features that don't necessarily need a maximum or minimum, so I went with rotary encoders with 2-bit quadrature. These rotary encoders cost $3.58 each and have 30,000 lifetime cycles. The rotary encoder filter circuit is shown here. It consists of 2 pull-up resistors, one for each connection, and then 2 RC filters, again, one for each connection. The X's in the middle show where the rotary encoder will be soldered onto the PCB.
Okay, so here we have the overall framework and function of switches and the knobs. So there are three rotatable knobs which are used to control the BPM, time signature, and flash or fade timing. And the switches are used to change the LED mode, turn on or off the dimming module, and the flash or fade mode. To begin with, the user initially selects if the mode should be operating in metronome or sensing. And in metronome mode, the user can choose the BPM and the time signature values. In sensing mode, the user can choose if the LED should stay dimly on or off, and the user can also select if the light should fade or flash. Then the user also can change the value of the flash or fade timing. Here's the software design, and we'll be using the Code Composer Studio to program the microcontroller. The output voltage we will be using is 3.3 volts, and the ADC module is available with this microcontroller, which will be used to take and convert the analog values to digital values from the switches and the knobs. And the UART module is used to send the data from the MCU to the USB flash drive. Here's the schematic that's created in Eagle that shows the connections, available connections for the microcontroller, which will be used to connect with the other components of the overall schematic. Uh, we finally came up with the option MSP430F46989 to be used in this project because we already had it available, and it was used for prototyping and testing. Um, this microcontroller has 40 pin module and the UART to store the data in the flash drive. The switches and the knobs requires 2 pins each, so overall 12 pins are required totally, and the LED output requires 1 pin, which is also available. And the interior sensors within the drum require 6 pins each, so 6 pins overall, and the exterior sensors are connected together requiring just 1 pin totally, which is sufficient enough for this overall project. For the user interface display, we decided to use the HiLetGo HD44780 display, which can display 16x2 characters, which is sufficient enough for the required objectives for the overall project. And it approximately cost $8.99, and which is for 2 displays, and although one is required, and it is also compatible with MSP430 microcontrollers. And here are the design constraints that we came up with as limitations and precautions during the project construction and also during the usage. For economic and budget, all materials that we acquired are from our own group's funding without exterior sponsorships. For the time constraints, we have only 2 semesters allotted, which is enough time, but there could be tiny deliveries to obtain the parts. And there are environmental constraints that all parts, especially hardware parts, should not create environmental waste such as that could cause pollution or toxicity. and which leads into the health and safety constraints, which such as the drum beats could cause hearing problems, and also the battery and LEDs could overheat, which could lead to explosion and the fusing of the LEDs. And there is a manufacturability constraint as well, which is that the overall project should be lightweight and small in scale so that it can be constructed effortlessly, and it has to sustain long enough until the showcase of the project.
All right, in this section we have the budget finance. On the left, you can see our original budget prior to the majority of our research and part selection. Our current budget is estimated to be about $355. That is calculated with the price of all the components we bought so far, plus an extra $100 for PCB manufacturing.
Here's our plan towards the project completion. First, we are planning on testing the overall PCB design and schematic, and then we'll start with connecting the framework of the infrared sensors and the LED strip array around the drum, and then soldering the parts to the PCB along with the separate LCD display as well. And then we will begin the coding of the MCU, initially to take the inputs from the sensors, and secondly to output the data to the LED strip array and the LCD display. And these are the official future plans, which is the project summary and the midterm demo and the conference paper and the project showcase, as well as the final documentation, which are the planned completion dates as per the official dates.
Thank you for watching. This has been the LUDS, and we are Group 10.